Howdy, folks. I'm Jeff. I'm here today to talk about agents and artificial intelligence in this exact point in time. I'm going to take the perspective of really trying to give you a practitioner focused view of what does all this stuff mean as we work today, and give you some guidance to how this translates into your career. So let's frame up what we mean by artificial intelligence. This is really our biggest lens to take. This is the whole field. This is really when we think about everything that comes under this bucket of being able to build machines which do tasks which we perceive intelligence being required for. There's a lot of formal definitions. This talk is a little bit narrower, so I'm going to just kind of zoom right past it. A lot of times how we do this is the largest subsection of the total field of AI is what's often called as machine learning. I'm going to give you a little bit more of a working definition in the next slide. Briefly, that means learning from data. And then lastly, one particular pattern that has emerged within the field AI more recently, based on some work that goes much, much further back, is this pattern of agents. This is really where we're going to center a lot of our sort of current today type conversation. All right. So let's just be a little bit more concrete about what we mean by machine learning, because I think everyone in this room has already been touched by machine learning, has already used machine learning in some fashion, but you may not have the best understanding of what fits within the box. Generally speaking, we think of machine learning as being the ability for a program to learn how to perform better from data. That's kind of it. We contrast this with writing code by hand, with a human insight deriving a particular behavior and then encoding that manually. Machine learning is all about autonomous algorithms learning directly from data. And then we really just say any time in which we can improve our performance from getting exposed to more data and machine learning has occurred. A lot of times we talk about models. Model is one of those words that can mean a lot of different things to a lot of different people. In the context of machine learning, we really mean a trained artifact of this learning loop. I'm going to have some diagrams to break this down for you a bit more. And the key thing here to underline is the behavior of the trained artifact here is really emerging from how you set up this learning process, not from handwriting those behaviors. And that gives it a big part of its generality and its huge impact on the economy we see these days. Okay, a little bit more about what we mean by training. This is a very, very abstracted diagram, but just to get us grounded on what we're talking about here is out there in the world, there is some data. That data can be anything. It can be pictures, it can be text, it can be code, it can be sensor readings from some exotic instrument. Lots of different categories of data. Off that data, we can apply a model. We can try to determine something of it. So if we've got images, we say, is this image a cat? The model's going to predict, and it's either going to be right or wrong. From that correct or incorrect prediction, we can derive a loss, that is, how far we are from the correct prediction. We then optimize our performance over that. That is, we change the model's internal state, often called its weights in a deep learning context, and then we continue our loop around. And so those weights are what persists each step of this learning. And so machine learning is built around the concept that this loop in and of itself will allow us to get better and better at tasks of interest, which are a really, really huge range of things, as I think most folks in this room should now be seeing in the world around them these days. This iterative capability, this ability to learn from data is really one of the most powerful techniques in the entire history of computer science. And it's really, really simple. And so I want people to kind of keep that central in their mind, because everything we're going to do is going to stack up much, much higher from there. Okay. We talk about what are models. This can be a really, really deep and hairy topic. I want to get you framed at least on these basics here. And so this is incredibly abstracted and probably not the way you would get introduced to it in the most formal sense. You can really think of there being two pieces to what is learned in a model. The first is the core algorithmics of the thing itself. That is, described here as almost even a recipe. It really consists of what are commodity common components. These are things like matrix multiplications, normalization layers, nonlinearities, most commonly a rectified linear unit. But also, so all of these are just kind of the core algorithmics. They're a pretty small amount of code. They're pretty comprehensible amount of code. They're easily shared. They're not very big. And very often there's a lot of the work in them came from research and is broadly shared by the entire community. When we run that loop, as you saw, we accumulate knowledge in each pass. That knowledge gets filed in what are called weights in some forms of machine learning. Those weights are are not human inspectable. They don't look like anything. They're just floating point numbers, as you see on the right there. But that's where actually all of the knowledge is persisted from the combination of this given architecture, which says that information is processed in a given way and then applied out to specific weights. The weights are where we really record things, and so that fusion of those two things is what's called a model or a trained model, and we really understand what that model does by applying it on new data, by testing it in some way. Now, a little introduction. I want to make sure that you have a clear understanding of what makes a model good, what makes a model powerful, what are the things that we need to be successful in building an ML model. The first and most important is data, and to get your head framed the right way, um, data is the basis for all knowledge derived in machine learning type approaches. The common data set used in something like a large language model, like the GPT model that powers ChatGPT, or the Gemini model, which powers the Gemini app, or the Claude model, which powers Anthropic's apps. Um, the common data set that you are using is the entirety of the internet. Every book that has ever been written, every newspaper article, every bit of research, every bit of poetry in every language, everything is basically in the raw data set. And so there's a lot of choices we have to make about how to use that. But one of the most like obvious consequences of that paradigm, of that way of working, that jumps out immediately is, well, if you're going to operate over basically all of humanity's knowledge, you're going to need an enormous amount of compute. A huge portion of the progress within the field of artificial intelligence and machine learning generally is that bigger scale approaches, things which unlock new possibilities, whether they be the introduction of GPU acceleration or clusters of compute or more efficient kernels or flash attention, whatever. These are ways of giving us more and more ability to compute over the data that we have. And so this drives a huge portion of the progress. It means a lot of very specific things about career paths in terms of what sort of companies can do what sort of work. Um, some of the things that are a little bit closer to like the core human work here is, so there's this huge body of human knowledge. We've made a huge portion of it, the majority computable in some fashion. But now we have to actually define our tasks, decide what it is we are optimizing for, pick our objectives. This is one of those things that spans quite a bit, from the academic end of the spectrum to the more industrial end. This is all of the how do we do this stuff. I talked a little bit about our architecture and the blocks of different methods that we use there, the different sorts of models. And so these are key innovations, things like the attention methodology and its deployment inside transformers. Before that, convolutional neural nets, which is a key part of how Jan won the Turing Award, to everything to how we train these models. And for example, if we've got all of this data in the world, we actually use a pedagogy, that is an educational philosophy for how to expose models to easy problems, then harder problems, then even harder problems, to build up intelligence in a particular capacity. One of the most interesting and hottest areas of intersection between AI theory and abstract computer science and how it meets the real world is evaluation, that last feature there. I know a ton of people working in this area, these areas that get a lot of budget, that have a lot of strategic importance to the organizations deploying them, and they span what I would call pure AI companies as well as academic research labs. But they also completely apply to every large corporate buyer, or even just individual. You have to know what models are doing in terms of their impact on the task of interest. And so if they are detecting fraud in your credit card transactions, you need some way of being able to measure that and knowing if the code that you shipped, the better model that you just trained, is in fact better, is in fact reducing fraud. Evaluation is one of the most critical and broadly present specialties within the field of machine learning today, and has a really big impact on whether or not you're going to do better or not. Can you measure what good is reliably, consistently, actionably? Okay. Last little bit here is I want to give you a little bit of a map of the lay of the land. And so, um, as I said, AI is bigger than ML, and ML is bigger than deep learning. And so there are a lot of different sorts of methods within the current sphere of AI in industry. What most people are typically talking about are connectionist approaches, most commonly deep learning, very often based on transformers and attention, which is to say a lot of these are based on the idea of statistical association, and that statistical association between some inputs and some outputs. And so that means particular sorts of problems where you have a lot of example coverage are going to be really, really amenable to these sorts of approaches. But another thing to keep in mind is all of these models are stochastic. That is, they are not simple if then else sort of statements. They're going to behave with a non-determinism that makes them not as well suited for some high stakes circumstances. And these are environments where you need proof, where there's a safety criticality. This could mean things like literal human life. So think of things like X-ray machines, like automotive, aerospace. Also things that are just really, really impactful in the world. Pricing models which deploy billions of dollars or pounds. Things which determine someone's access to credit or housing or education, things like that. And so connectionist paradigm, which is the dominant one we work with in today, is not always the best fit for things which are at that edge there. But this is something to keep in mind is that we do today those things which are amenable to having lots and lots of examples and are not necessarily at the most extreme end of high stakes. High stakes is where you start to see the limits of what AI/ML can or cannot do, and you need to be really concerned about when and how it's being deployed and what roles humans are playing. We'll talk a little bit more about that in my vision in a little bit later in this talk. One thing to keep in mind is a lot of this talk is going to be very agent first. I'm talking to you about the things that AI needs and AI is good at. But I want to keep in mind here that none of this is truly autonomous. It is not self-creating. There is always a human in the loop that is driving this work, that is defining what are we trying to do, what data should we use, how should we measure our progress against it. And in every single instance of successful ML application, it really is this iterative refinement of a human's intent, a human's attempt to approach this with an ML model's passing through of that data and improving its performance. This is a constant collaboration. And I don't mean to anthropomorphize this more than this is. And so the thing on the right is just math deployed at extraordinary scale with computers. That's it. But this ability to extend your human intent into that abstract representation is a huge extension of your intelligence and your capability. And so it's really important to think about like all these technologies we're building to make them better. We make them better to be in service to you, the human author. All right. So to get a little bit narrower into our specific main character of the rest of this story, we need to talk about agents. This is one of those areas where I like to talk about it, but I also get a little bit frustrated by the terminology because it makes me because we have to start with sort of pulling apart the two definitions of what is an agent. So back in the day, and by back in the day, I mean, generation or two ago, we conceive of an agent as something very specific. And so an agent was this computer science abstraction that lived in a box and was somewhat anthropomorphic. And it interacted with an outside world, an environment, and in its world state. And it has two sort of interface boundaries. It can perceive the world, and so it has some ability to take in new knowledge. That could just be text, as in something like a chatbot. It could actually be vision, as in something like an autonomous robot, or a mixture of many things. With the agent's sensors, it can recognize that data. It then alters its understanding of the state. It applies a policy, it decides what to do next, and then it actuates on the world. That place people will come across this is in a classic AI textbook from Russell and Norvig. Highly recommended. This is the really traditional view of things. It's very anthropomorphic, meaning this is modeling a computer science concept as if it were a person in a way that gives us a sense of what are the pieces and what are our design spaces. This is how we thought about agents for a long time. This is not what people mean when they say agents today. Agents today are a somewhat simpler concept. They still perceive the world, they still act on the world, but in the middle, we don't necessarily have the same complexity to the machinery. Inside is not actually a learning loop typically. What instead we have is just a generation operation that is often going to a cloud-based LLM, oftentimes a commercial model. And this model isn't changing in response to things. And moreover, the model doesn't actually have a memory. And this is one of the things that can be a little bit deceptive when people are introduced to the concept of generative AI within the context of, say, a chat application, is it behaves as if it knows who you are, knows what you just talked about, can continue a conversation from step to step to step. But in fact, in this yellow generation operation here, what's actually happening is that there's a complete amnesiac there. On every single operation, it is replaying the entire history of everything you have ever said it to, and it is just discovering you and your problem and your specific context and the state in the conversation on every single new operation. It has no sense of memory. It does not persist or take a further action. And so it's really kind of an interesting little trick on the inside. One of the consequences of this is there's no learning loop there. There is no policy being updated. All there is stacking more and more context. That more and more context could be used for other things. I'm going to show you an example of one way to do that. But the common agent that you're interacting with today that has a huge impact on what we can build today across a wide range of applications functions like this. All right. And then I want to do just a little bit more turning towards making sure that we put all of this in career context. A big part of this work in general is solving the next problem. And I do mean that whether you wind up closer to the academic end of the spectrum or more to the industry end of the spectrum, because the impact of agents and commercial grade generative AI means that we are constantly consuming things that we have figured out how to solve and turning them into more efficient representations. Historically, we would have done that through simple libraries and things like that, deterministic automation of tools and things like that. And so if you've been on GitHub, you know that there are tens of millions of distinct projects that people have given away to the world for free because they cannot actually derive a direct revenue from them. They are literally commodities, and so they're abundantly provided to the world for free. The work of AI often accelerates that move from things which we just figured out how to do into something that is now repeatable and easy to reuse. And so we're constantly kind of at that boundary of the next piece of work you'll get assigned for new work that you can do to get paid in a job, in a company, or to publish a paper is just past that boundary, but is going to get rapidly pulled back. And so a key part of the skill of working within an environment that is in any way touched by AI is understanding how to reach for the next thing, how to frame that next problem, how to deliver a new solution that really kind of pushes things forward, because you're going to need to keep doing that and doing that and doing that as technology moves forward. Because once we've solved something, it becomes very, very cheap, very, very low cost, and it becomes very hard to build a career around that. And so our job here is to figure out it's about you. And so we've talked a lot about agents, but I want to connect this back to agency. Your choices, the things that you get to decide to do in your career. I have been working in this field for over 20 years at this point, and I have been told at various points in times that this thing is the technology that's going to change everything, and that everyone swarms on this. We spend huge amounts of human labor and attention on working with this particular technique. I don't know, something like maybe 14 years ago or something, I was in New York and everyone was working on random forests, and these are these tree-based models, and we were trying to figure out these features that might exist in your browser, and then if we could build the right tree, we would understand you're going to click on the ad and you're not going to click on the ad. And tons and tons of people worked on this work and just all of the moving around of data. And then things moved forward and forward. And so we start to build conversational models using things like semantic parsing or probabilistic graphical models. And these things are incredibly hard, and they never really achieve quite what are needed. But then we spend so much attention on it, and then the deep learning era comes along. Things start to really, really work. And so this is techniques like convolutional neural networks, recurrent neural networks, LSTMs, eventually transformers and attention, and then forward and forward, flash attention and reinforcement learning. These days, we're working on agents. Agents are trying to pull together more and more of this work. This line will keep going. It will keep moving. What this chart might look like at the point in which you enter your career, you start working, will be different, and it will keep building. And so my point to you is that this is the sort of never-ending progress of technology. There's always a new challenge that's going to come up. These are opportunities to take on new challenges. And you have to be prepared for this sort of ceaseless discovery. And I think it is an opportunity. I do want to be concrete and sort of address you directly, because I do spend a decent amount of time speaking to students and early career people in different contexts, and I hear from them that they can feel like there's something of a broken ladder here, that it's hard to get first roles, it's hard to build good experience, and that a lot of the things that people said, oh well, this is what you're going to work on your first job, those end up getting chewed up in some way. Maybe we made them more efficient with a bit of AI. Maybe we shoved them into someone else's job because it got easier in some way. We use software for that thing, and we don't actually need to hire a person to work on that. It's a real challenge. I'm not gonna deny that one. I don't have all the answers, but I'm gonna give you my perspective on some of this, because ultimately there is a higher part of the ladder. So you have to understand which part you're grabbing on to really deliver value. The first thing I want to say is I'm giving my thoughts, but ultimately, you're the person who walks out of this room. You're the person who is in charge of your own career. You have to decide what you want to work on in your career. You have to decide what is good work. You have to figure out how to attack it, and you're the person who's going to own this outcome. And I really mean that, like, I really mean all of this within the context of having superhuman intelligence in your pocket at all times, competing with people who have those exact same capabilities at all times. The AI that extends your capability does not remove the ability of you to discover new problems, to frame them differently, to achieve new outcomes that no one else has achieved before. It actually amplifies your ability when deployed in the right fashion, and only you can drive that work. I have some general moves I would recommend people to consider. Some of those is just like picking a good problem. I'll be blunt here is that, like, the best careers I know about are from people who just kind of made them up themselves. The people who just picked them out, who chose the problem they want to work on, and to actually go out there in the world and propose actual solutions to that. Propose that in writing. Propose that in real work. Public artifacts of your work, the legibility has a huge impact on who you get to work with, what they understand about your abilities, and the opportunities that open up to you. And so, when I talk about having reach here, one of the things you could do is you could, hop on a camera, you can give a talk, and you can hang on YouTube or TikTok or something like that. But you can also just build in public. You can make useful software and give it away to the world. You can talk about your learning experiences. And ultimately, you can earn your seat at the table mindset. Lastly, I'll leave you with this. I think a lot of times when people look at, like, this rapid pace of technology, they can wind up in the pie model of the world. And I understand why this is easy. It's just like, there's all this stuff that could be built. Oh, and then someone built it, and so now there's this good social network, so no one needs that social network. Oh, there's this good video streaming site, so no one needs a video streaming site. No, there's a mobile operating system, what have you. And that's the fixed pie size of the world as we're gobbling all this stuff up. I don't believe that. I believe we are on a frozen alien planet so vast that we will never see the edges of it, and we're just barely getting past the bits of thawing ice to be able to discover the rest of the world. Every new discovery opens up so much more new territory for all of us to build and create new things. And that's just going to continue for the rest of our lives. That there is no finite pie of all knowledge that somehow is getting chewed up. There's no finite pie of all the technology to be created. If you want to work in a space that is being really driven by all of the advances that come from AI and its ability to learn and achieve things beyond what you can do directly, to expand the scale of your human intent to accomplish new tasks. That's a superpower, and it allows you to go out further and further and to see even further than people had done earlier in the history of technology. And I think that's really how I would frame the work of AI going.